Hello, everyone. My name is Kaivan Kamali. I'm a member of the Galaxy team at Penn State University. This is the introduction to recurrent neural networks. This is part 2 of a 3-part series on deep learning. So the requirements for taking this course, if you will, there's introduction to Galaxy analyses. That just basically tells you how Galaxy works. There's an introductory deep learning tutorial, which would be nice if you complete that tutorial first. And there's also the first part of this 3-part series, Deep Learning Part 1, Feed-Forward Neural Networks, that you should definitely complete before starting this one. So the questions that we're going to ask is, what is a recurrent neural network and what are some applications of RNN? And our objectives are understand the difference between feed-forward neural networks and recurrent neural networks, learn various RNN types and architectures, learn how to create a neural network using Galaxy's deep learning tools, and solve a sentiment analysis problem on IMDb movie review dataset using RNN and Galaxy. The last 2 bullets, they're part of the hands-on or lab section of this tutorial. So what is a recurrent neural network? So recurrent neural network models sequential data. The data could be temporal or ordinal. And in recurrent neural network, training example is a sequence, which is presented to the neural network one at a time. One example is a sequence of English words that's passed to an RNN, one word at a time. And the RNN in turn generates a sequence of, for example, Persian words, one at a time. So in RNN, output of the network at time t is used as input of the network at time t plus 1. And this could happen this happens for the duration of the sequence. So your sequence could be of size 5. So the output of the first timestamp goes to the second one, output of the second timestamp goes to the third one, all the way to the 5th timestamp. So our RNNs are mainly applied in image description, machine translation, sentiment analysis, and so on. So there are different types of RNN architecture. There's obviously one-to-one, in which you have one input and one output. That's not really any different than a typical feed-forward neural network, where if we have a sequence of size 1, we basically don't have a sequence. But so that's not, we don't have a slide for that. But the next one is one-to-many, in which we have one input and we have a variable number of outputs. So for example, in image captioning, we provide one image and we get a sequence of words that describe that image. So for example, if we pass this image in, we're going to get a dog on the couch back, which it's one input, 4 outputs. We could also have an RNN such that we have many input and only one output. Again, the number of input could be variable. The one example is movie reviews. So movie reviews are a collection of text, and we want to classify movie reviews into positive or negative. And our output is just 1. It's basically a bit, could be 0 and 1, representing 1 maybe representing positive review, 0 representing negative review. So if a review is such a bad movie, obviously that's a negative review. So we discussed one-by-one recurrent neural networks, which are basically a feed-forward neural network, one-to-many and many-to-one RNNs. And next is a many-to-many RNNs. There are 2 types of many-to-many RNNs. One is that the number of input and the number of output match. So for example, let's say you are tagging every frame of a video. So the number of frames and the number of tags match each other. So let's say you have 1,000 frames and you would have 1,000 labels to tag those frames. So that's a simple case, but there's a more complex case in which a number of inputs and outputs do not match. And this happens in machine translation. So for example, you have a text in one language and want to translate it to a different language. And you know, if they don't necessarily have the same number of words. So for example, here we have 3 words in English that are how are you, and in Italian we have, I think, come va, which is the equivalent. So it could be the other way around, that the number of input words is less than the number of output words as well. So that's the 4th type of RNN in terms of the number of input outputs that they can take. So there are basically, you could say, 3 types of RNN architectures. There's a so-called vanilla RNN, which is basically what we've discussed. And RNNs have a problem in that they suffer from the vanishing gradient problem. We discussed the vanishing gradient problem in the part 1 of this deep learning series. So if you remember, we calculate the error initially at the output layer, and then recursively we can calculate the error in the prior layer and continue so on until we get to the input layer. And every calculation requires multiplying the derivative of the activation function. And because we were using sigmoid, the derivative of the sigmoid is mostly very small numbers. We're going to be multiplying multiple small numbers to calculate the error factor for the initial layers of a neural network. And multiplying many small numbers results in a very small number, and that decides how much we change the weights. So because we change the weights by a very, very small amount, the learning algorithm basically halts and cannot progress. So recursive neural networks, the vanilla version, which has no basically remedy for this problem, obviously suffers from this problem, because sometimes we have very, very long sequences. We have like hundreds or thousands long sequences, and they definitely cannot be trained. So there were like a couple of solutions where one is called LSTM, that stands for long short-term memory, if I'm not mistaken, and GRU, I think it stands for gated recurrent unit. I could be wrong. I'll double check that. Anyway, LSTM was proposed in the 90s, and it's still used. So if something was proposed 20 years ago and still actively used, that tells you how good it is. And GRU is a simplification of LSTM. So what they do is, in order to avoid multiplying gradients to decide how much we update the weights in the initial layers, they introduce these things called gates. And while the math is beyond the scope of this tutorial, introducing these gates results in adding the derivative of multiple activation functions to update the weights in the initial layer instead of multiplying the derivative of activation functions. So if you multiply multiple small numbers in each other, they will quickly become very small. But if you add multiple small numbers, well, they become small at a slower rate. So this means that LSTM and GRU does not suffer as much from the vanishing gradient problem, and they can potentially model sequences of length thousands. So they're pretty powerful. LSTM has 3 gates. There's a forget gate, update gate, and output gate. GRU is a simplification of LSTM. And it has some benefits because it has fewer gates, it has fewer parameters, so it's easier, less computationally intensive to train it. But they're both very good. So anyway, that was a little bit of info on LSTM and GRU. So sentiment analysis, as I mentioned in one of the slides before, we want to perform sentiment analysis on IMDb movie review data set. So we want to train a recursive neural network on the training data set. There are 25,000 reviews. Some are positive, some are negative. After we're done training, we want to evaluate our model on the test data set, which is again 25,000 reviews, some positive, some negative. There is no overlap between the training and the test data sets. And we're dealing with text data. So it's a good idea to review mechanisms for representing text data. So the first step in text processing is the pre-processing step. That is, we want to clean up our data. We first tokenize a document. That is, we break a document into words. That's step number one. We remove punctuations, URLs, and stop words. And stop words are words that are very common in every document, and they don't have much value because they don't help us discriminate between documents. They're kind of like noise, so we have to remove them. So English language has a lot of stop words like any other language. So the stop words in English language are a, of, the, and such. So these need to be removed. We also remove, obviously, punctuations and URLs. Then we're going to normalize the text. That is, we replace BRB with be right back and so on. So different ways of representing the same thing are eliminated. We only have a single way of representing these. We run the spell checker to fix the typos, and we make everything lowercase. So that's the pre-processing step. The next step in pre-processing is called stemming or lemmatization. So let's say you have multiple words like organizer, organize, organized, and so on. We don't want multiple words in our feature set representing basically the same word. So what we do is we want to reduce all of them to a single word, and we're fine with that. So there are two ways to do that. There's stemming and there's lemmatization. So stemming basically cuts the end of all these words, organizer, organize, and organize, and comes up with a common single root. So we come up with organize without the E. And as you can see, it's not an actual word. So lemmatization is the same concept, except that it's smarter. It's actually using the meaning of these words to come up with a common root that's actually a word. So that's so lemmatization a little bit more advanced, if you will. Takes into account the meaning of the words, whereas stemming is just cutting the end of the various words to make them have a common root. So after that, we can use a couple of models to represent documents if we're dealing with documents. So one model is called bag of words, or BOW. And if you don't care about the order of the words in a document, you use a bag of words model. It's basically a two-dimensional array, a matrix, if you will. So the rows represent the documents and the columns represents all the words and the vocabulary. That is all the unique words in all the documents that we have. So if a word is not present in a document, we put a 0 in the corresponding row column representing the word on the document. And if the word is present, we can put 1, or we could put the frequency of the word, count of the word, or even better, the frequency, which is kind of normalized. So let's say if the word is there, we put 1. If the word is not there, we put 0. The word is there and repeated 5 times, we put 5. That's word count. And the frequency, if it's like the word is there 5 times, but the length of the document is 100. So we put 5 divided on 100, over 100 as the frequency. So this is one example. So let's say we have 2 documents. One of them says Magic passed the basketball to Kareem, and the other one says LeBron stole the basketball from Curry. So we have 2 rows representing document 1 and document 2. And we have 2, 4, 6, 8, 10 columns representing all the words in these 2 documents. And we're just using 1 and 0 to represent whether a word is there or not. And as you can see, we did not remove the stop word. So this is like a simple example just to show you what bag of words is. So bag of words is simple, but it does not consider the rarity of a word across documents. So if a word is rare, it's present in certain documents and not in the other one, it has more power and for discriminating between documents, but bag of words, doesn't capture that. So there's an alternative representation called term frequency inverse document frequency. Again, this is when we don't care about the order of the words in a document. So similar to bag of words, we have an entry for each document word pair, and entry is term frequency. So that's similar to bag of words. That was one of the options there, but it is multiplied by inverse document frequency. So that is the number of documents that have a specific word divided by total number of documents inversed. And we usually take the logarithm of that too. So if you multiply these two, you get term frequency inverse document frequency. There are usually like a +1 or plus epsilon, a small number, added to these two elements to take into account situations when a word doesn't exist, or deal with the corner cases. Okay, so one-hot encoding is a way of representing one word. And it's basically a technique to convert categorical variables such as words into a vector. So let's say our vocabulary is of size 3. We have 3 words: orange, banana, and apple. And each word is then represented by a vector by the size of the vocabulary, which is 3. But the idea is that orange, only the first element is 1, everything else is 0. For apple, the second element is 1, everything else is 0. And for banana, the third element is 1, everything else is 0. So these vectors represent unique words in the vocabulary. The problem is if the vocabulary size is big, then we're going to have a lot of zeros, and this is going to require a lot of storage. So if we have like 10,000 words, then these vectors will become of size 10,000. And the other problem is that we don't have a concept of similarity between these words. So finally, there's word-to-vec algorithm in which each word is represented as an n-dimensional vector, and n is much smaller than the vocabulary size. So we said if we have 10,000 words, in one-hot encoding, every word is represented by a vector of size 10,000. Whereas here, it is represented by a vector of size n, which is much smaller than the vocabulary size. Let's say n is 64 or 128 and so on. But the word-to-vec representation has the nice property in that the words that have similar meanings are closer to each other in the vector space, and the words that don't have similar meanings are distant from each other in the vector space. So how do we define similarity? So we say that the idea is that the words are similar if they co-occur often in documents. So we have obviously a lot of documents. We can use those documents and take the idea that words that co-occur have similar meanings to define similarity measures for all the words in the vocabulary. There are 2 algorithms or architectures. One of them is called continuous bag of words, where you predict the probability of a word given the surrounding words, or as it's called, the context. Or there's another algorithm called continuous skipgram, where given a word, you calculate the probability of words surrounding that word, which is the context. So you can basically use these algorithms on a document database and come up with a word-to-vec representation for all the words. So sentiment analysis or sentiment classification, we want to determine whether an IMDb movie review is a positive review or a negative review. And we have a data set which has a mix of both positive and negative reviews, and we want to use a recursive neural network to basically come up with a model. So we train a recursive neural network using IMDb movie reviews, and the goal is to learn a model such that given a review, we can predict whether the review is positive or negative. So we also have a test data set that's not used in training, and we use it to evaluate our model. And we plot a confusion matrix, which is a way of evaluating classifiers. Okay, so that's the slides. The references are in the tutorial. The tutorial, if you go to training.galaxy.org, that's the main Galaxy Training website. If you scroll down, these are different topics. If you scroll down to statistics and machine learning, and scroll down again, you would see the RNN tutorial. This is part 2 of the deep learning series. And if you scroll all the way down, you'll find the references here. So these are the references. It's just not a good idea to put all these in a slide. So some other information, as I mentioned, training.galaxyproject.org is the main website for Galaxy Training, various topics, tutorials, and contributors. You want to get help, please go to helpgalaxyproject.org or use one of the Gitter channels listed here. And these are the list of events that you can find at galaxyproject.org/events. So the next step would be the hands-on section of this tutorial, which I will do in a separate video. Okay, I will see you soon. Thank you. Okay, so we're gonna start the hands-on section of the recursive neural network tutorial. As always, you have to go to training.galaxyproject.org. That's the main page for Galaxy Training. And go down to statistics and machine learning. And here we have recurrent neural networks tutorial, which is a part 2 of a deep learning series. So if you click on the slides, if you scroll down, there's a section to get the data. So as before, we do have the workflow for this tutorial here. So all of the steps that I'm doing, they're going to be basically part of a workflow. You could download this workflow, upload it, import it into Galaxy, and run it. But here in the hands-on section, I'm going to go over all the steps that constitute this workflow. So let's go back to the get data section. We're going to copy these links. We're at usegalaxy.eu. We have to create, this is a new history. We have to give it a name. Let's give it a descriptive name, GCC 2021 RNN. And what we do is we click on upload data, go to paste/fetch data, and paste the links to our training and test data set. So we can close this. These files are going to be uploaded into Galaxy. There are 4 files, 2 for training, 2 for testing. One of them is the feature vector. Well, it's basically a training set. The other one is the label for that training set. Or yeah. So these files are a little bit large, but we'll wait while they upload. So these are IMDb movie reviews. So movie reviews, there's 25,000 of them used for training and 25,000 of them used for testing. What we did was for pre-processing was that we skipped, we ignored the 50 most common words in the reviews. Those are the stop words that, you know, like add, the, of, and so on, that don't have much value. And each review is limited to 500 words. So if the review was longer than 500 words, it would get trimmed. If it was less than 500 words, it would get padded. So let's see. Okay, so the files uploaded took a little bit longer than usual. I paused the video. So what we need to do is that we have to rename them by getting rid of the extension and the URL part of the file name. And we have to make sure that they're of type tabular, which in this case it is. So we're going to repeat the same thing for the other 3 files. Check the data type. It's not tabular, so we click here, select tabular as an autocomplete and say change data type. And we'll do the same for the last file. Okay, so this should take care of our training and test data sets. Both the labors and the feature vector. So let's go back to the tutorial. So we go to step number 1, create a deep learning model architecture. So I know that pretty much all the tools that we use are under machine learning, which is under statistics and visualization. So I click on the left-hand side, which is the tool panel. I'm going to click on machine learning, and I'm going to say create a deep learning model architecture using Keras. So that's what we want to do. So I'm going to look at my notes here to see what exactly is the layout of the neural network. So we don't diverge. So the input shape is 500. That's correct, because we said that each review has maximum of 500 words and is trimmed if it's longer and padded if it's shorter. So layer 1, we add an embedding layer. So this is embedding. If you search for it, embedding, we may have passed it. Maybe not. So, Okay, sorry for the technical difficulty. It seemed like the embedding layer was not in the dropdown, but as I started typing here, it showed up. So that's it's good to know. If you start typing here, all the matching type of layers would show up. So the input dimension is 10,000. Our corpus, well, it would be basically all of our movie reviews have 10,000 unique words in total. So that's our input dimension. What we want to do is we want to reduce that 10,000 dimensional data to 32 dimensional data, which is more, we don't want the search space to be too big. It would result in unnecessary storage. If you want to represent thousands of words and each word is represented by a vector of size 10,000, obviously the storage requirements will be much more if you have thousands of words and each are represented by a 32-dimensional vector. So this embedding layer does that. It takes our 10,000 dimensional document for 1 dimension for every word into a 32-dimensional space. So we're going to insert another layer. The next layer is going to be a recurrent. So this time I'm going to type. So we're going to pick LSTM. The number of units is 100. So the output the state and cell information, they're all 100 dimensional. And we add another layer. It's going to be, this is the output layer. So we're going to leave it as core dense. We're going to have 1 unit, and it's going to be sigmoid. So this is basically if the output is greater than 0.5, we assume that it's a positive review. If it's less than 0.5, we assume it's a negative review. So let's double check. Our input shape is 500. First, we have an embedding layer that takes the dimension from 10,000 to 32. That's correct. And we have an LSTM layer with 100 units, and the core dense layer with 1 unit and sigmoid. So this is good. We're going to click execute, and let's look at the tutorial and see what we should do next. So after this is what we just did, create a deep learning model architecture. Now what we should do is we're going to create a deep learning model. So this is another tool under machine learning. So this is queued to be run, but we can find the other tool, which is this one. Create a deep learning model with an optimizer, loss function, and fit. And our job is running now. So we need to create a building mode is build a training model. The default value is fine. Select the dataset containing model configuration is the result of the previous job number 5, was just completed up here. So we'll leave that as a default. Do classification or regression, we're doing classification. And then select a loss function. We use binary cross entropy because this is a binary classification. Either the review is positive or negative. And for optimizer, we generally use Atom because it has momentum, and it also has different learning rates for different dimensions, which could possibly have different scopes. And we leave the metric as accuracy. Epoch, we set it to 2. That means we're going to use the 25,000 movie reviews twice to train our model. And we're going to make the batch size 128. That means after presenting 128 movie reviews to our neural network, we're going to update the weights. So that's a mini batch gradient descent. We don't want to update our weights after 25,000 reviews because that's going to be too slow. We don't want to update it after just 1 review because that's not necessarily going to be accurate. So one of them was, this is basically a middle ground solution. So I think this is set. We're going to click on execute and wait for this to run, and we'll look at the tutorial to see what's the next step. So the next step is deep learning training and evaluation. Let's go and find that. So here it is on the left-hand side in the tool pane. I click there, and if you look, select the scheme as train and validate. We'll leave it as it is. Choose a dataset containing pipeline estimator object. That's object number 6, which is the job right here that's running and just completed. So next is select the input type. Our data is all tabular, so we leave it as it is. And we pick the training data set, the feature vectors, which is xtrain. Does it have a header? I think no, but we can verify. And then we select all the columns. And for training labels, well, the correct one is ytrain and doesn't have a header. We select all columns. And so I think I just double checked everything. It looks good. We can click on execute. So let's go back to the tutorial. So, so we define the layers of our neural network here. We defined what kind of loss function, optimizer, metric we're using, and also some parameters like epoch and batch size. Here, we're gonna train and evaluate on the training data set. And finally, the next step, we're going to use the trained model to basically predict movie reviews on a test data set. So let's see if this completes. This step may take a while because we have 25,000 movie reviews, and we're using our epoch as 2. So we're going to use that 25,000 movie reviews twice to train our data. So we have to go through 50,000 movie reviews. So it may take a while. Okay, I paused the video while the training was ongoing. It took about like maybe 10, 15 minutes for the training to complete. So you should expect a similar, time for the completion of the training. It obviously depends on the load of the server. This is obviously a bit more realistic example. And the feed-forward neural network hands-on work with a much smaller data set. This one, we have more training examples. Also, our training examples are higher dimensional. For like serious machine learning problems that are solved with neural networks, you may have to wait for possibly days for the training to complete, and you probably need to run the training on GPUs instead of CPUs because they can perform certain mathematical operations faster. So this is complete too. Now let's look at the tutorial. So the next step is model prediction. Basically, now that we've trained the model, we present it with some data and we'd see what it predicts. So we give it some movie reviews and we see if it predicts those movie reviews as being positive or negative. So we go to model prediction. Again, it should be under machine learning here. So you see the machine learning header here. Let's look for model prediction. Okay. And we leave, choose a data set containing pipeline estimator object. That should be, so one note, the previous job that we ran created 3 things. One is this, the evaluation, like how did the model do? The second one is the model, and the third one is the weight of the model. So 2 of these are used in this job, the model prediction. So here, we care about the model itself, which is the result of job number 8. Here, we care about the weights, which is the result of job number 9 here. So we assign these 2. We leave the invocation method as predict. I'm double checking my notes, which is basically this tutorial in a separate window, just to make sure every parameter that I pick matches what we have here. So that's what I'm doing. So the input data is obviously tabular. The training, we provide for testing, we provide X_test. It does not have a header, and we select all columns. I think this is ready. We're going to click on execute, and this is going to take on 25,000 movie reviews and provide a prediction for all of them. So we should get 25,000 ones and zeros. 1s for positive reviews, 0s for negative reviews. Okay, so testing, passing the test data to the model took obviously much less. Maybe this would took like 5 minutes, which I paused the review. So if you look, we should have a bunch of 1s and 0s here. Which are the predictions of our model. As you can see, there should be 25,000. So let's see what's next in the tutorial. So we have to now visualize how our model performs, and we do that by creating a confusion matrix. So this happens with a machine learning visualization extension tool. We're going back to tool pane. If we scroll down, there's a statistics and visualization header. Under that, there's a statistics, machine learning, and graph /display data. So click on that and find machine learning visualization extension. You could type it here as in the search bar. I'm just, because I know where it is, I'll just directly go to the tool. So let's see if we can find machine learning visualization extension here. Let's see. Okay, it seems like machine learning visualization extension is actually under machine learning. So in usegalaxy.org, it was under graph and display data, but in EU, it's under machine learning. That's okay. I mean, some of these tools, they are basically under different headers, and that's fine. As long as you can search for them and find them, you're good. So we click here, the selected plotting type. We want confusion matrix for classes. So select dataset containing the true labels. So we pass the test data to our model. Now we need to provide the labels for the test data, which would be Y test. It does not have a header. We select all the columns in that file. There's only one column, which is 0 or 1. And then select dataset containing predicted labels. That's the output of our previous step. Does it have a header? Yes. And I think that should be it. We should execute this and get a confusion matrix. So what is a confusion matrix? While this job is running, let's take a look. So this is a confusion matrix. The x-axis has the predicted labels. So this line represents the counts of class 0 being predicted. So our classifier predicts 1281 plus 10397 class 0s and 1129 plus 2103 class 1s. Okay, so those are the predictions. The Y label are the true class labels. So these are the true across, these are the true class 0s, and these are the true class 1s. And class 0 and 1 in our example, class 0 is like a negative movie review, class 1 is a positive movie review. So if you add those numbers up, we have 12,000, let's see, 12,000, like 400 and some change negative reviews, and some number close to that positive reviews. And if a movie is negative, if a movie is if a review is a positive review and we predict it as positive, that's a true positive, shown in the bottom right corner in the green box. If a review has a negative, if a review is negative and we predict it as negative, that's a true negative. That's top left corner. So this is true positive, this is true negative. So if you predict it as positive and it is actually negative, that would be a false positive or type 1 error, which is the top right corner. And finally, bottom left corner, if it is a positive review, but we predict it as negative, that's a false negative review or type 2 error. So this basically quantifies how our classifier works in terms of positive and negative reviews. I mean, the same thing could be applied to, let's say you're trying to see if a patient has a disease or not. It's basically, it's again a binary classification. We would have a similar layout. Let's see if the job completed. I think it has. Let's view it. Okay, so this could be slightly different. That's what's in the tutorial, depending on how the model was trained and then how it performs on the test data. So, so how can we use this confusion matrix? Well, we've come up with two measures called precision and recall. Precision is basically the model predicts certain movie reviews as positive. What percentage of those are actually positive? That's precision. And it's defined as true positive divided by true positive plus false negative. And then we also have recall. So recall is, let's say we have 10,000 positive reviews. We want to know how many of those 10,000s are actually classified as positive reviews. Like, do we get like 8,000 of them or 5,000 of them and so on? So recall is true positive divided by true positive plus false negative. So we can calculate these two values. And I think we do that right here in the tutorial. And sometimes it's easier to deal with one number instead of two. So one solution is to use the F-score, which is the harmonic mean of precision and recall. And that's the formula for it. 2 times precision times recall divided by precision plus recall. So that gives us one number. So this is a harmonic mean. There's other ways you could use a geometric mean, or, you know, there's a host of techniques for evaluating the classification results, but usually F-score is fine. Sometimes, you know, you just look at the precision and recall and don't even bother creating the F-score. So if you go back here, we see that our classifier actually does pretty well because let's say it predicts, when it predicts a review as positive, among them, 10,160 are indeed positives. Those are true positive. Only 1,578 are not. And when it predicts a review as negative, 10,922 are indeed negative. Only 2,340 are not. So if you have a perfect classifier, we should have 0 on top right and bottom left. And the numbers on bottom right and top left should add up to be, you know, our test set, which in this case is 25,000 movie reviews. So in conclusion, in this tutorial, we reviewed feed-forward neural networks, explained how recurrent neural networks are different, discussed various neural network input-output types and architectures. We discussed various text representation schemes, and we solved a sentiment classification of movie reviews based on IMDb movie review using Galaxy's deep learning tool, which employed Keras under the hood. Okay, so the next tutorial would be the convolutional neural network tutorial, or CNN, and that will be next. Thank you.